Hello and welcome to this lecture in this series of applied statistics lectures from the statistics group at Aalborg University. Today's lecture is about estimating proportion, and my name is Ive Rubak, and I'll be presenting today's lecture. First I'll talk a bit about the scientific problem, and then we'll look at a sample proportion and its distribution, and discuss how that's related to confidence intervals, and finally we'll look at some data and make a conclusion. And first off, the scientific question is about placenta previa, which is a medical condition occurring in approximately 0.5% of pregnancies. And the setup is a medical researcher wants to look at whether this is related to the gender of the child. Is the proportion of girls different in placenta previa births than for births in general? And as background knowledge, we know that in the population 48.5% of babies are girls, so it's slightly non 50-50. There are slightly more boys born and less girls born. And for this medical condition, and to see how it can be a problem in connection to a birth, there's a figure here in the bottom right hand side where we see that there's an issue with the placenta being obstructing the birth of the child. And regarding the data, the researcher plans to obtain a simple random sample of the gender of n placenta previa births. So there's a specific number of births that we're going to check, and we know the birth has been in the presence of placenta previa condition, and we check whether it's a girl or a boy. And we haven't looked at the data yet, we're just trying to prepare how are we going to make a statistical analysis of this. And conceptually, the data is as in the table here, where we just get one row per baby containing an ID and the gender of the child. And then we augment this by a kind of dummy variable y, which just indicates whether we have a success or a failure. And in this case, we characterize, since we're interested in the percentage of girls, a girl is a success marked by a 1, and a boy is a failure marked by a 0. And for the entire population of placenta previa births, we denote this proportion by pi. So how many percent of placenta previa births end up in a girl being born? And that proportion is what we're really interested in, and that's really the population mean of the variable y. And this proportion is unknown to us. And the sample proportion pi hat, indicated with this hat above the pi, is telling us that this is an estimate of the true population parameter that we're interested in. And to figure out an estimate of that, we just count how many girls do we have divided by the number of births in total. And to count the number of girls, we can just add all the y's together. So we get a 0 for each boy and a 1 for each girl, so we get the girls counted, and we divide by how many we had in total. So really, we're looking at a sample or at a sample mean, the average of the variable y. That's the same as the sample proportion, and this gives us the possibility of using the central limit theorem in the next slide. And we really have to think about the fact that this pi hat is depending on the specific sample that we're looking at. If we get a new sample, we get a new pi hat, we get a new number of girls that are in that specific sample. So the pi hat is a random number, and the distribution of this random number is due to the central limit theorem can be characterized approximately by a normal distribution with the mean value of the true population proportion pi and some standard deviation, which is the standard deviation of the population divided by square root of n. So the standard deviation will be smaller with the larger sample size. So whenever we take a sample, we get a number of girls, we divide by n, and then that gives us a specific proportion. And here in the bottom we see the expected distribution, what we would get. So most likely we'll get something that's true, close to the true population mean. And so if I take one specific sample, I might get a sample here. The horizontal axis is it's a number axis giving us the numbers between 0 and 1, with pi here in the middle being the population proportion. And if I take a new sample, I might get a new value, and if I take another sample, I get another value. And most likely I will get values here in the central area of this normal distribution. That's what the central limit theorem tells us. Sometimes I get values in other places as well, and a rare once in a while I might get a sample out here, but they'll be nicely symmetrically distributed around this one. And to take advantage of this, we need to know that this approximation only is valid or is fairly good if we have enough both successes and failures in the data. If a success or failure, if observing a success or failure is a very rare incident, then the normal distribution can no longer be used as an approximation. But if it's not extremely rare, so let's say we have a sample where we have at least 15 failures and at least 15 successes, so that would be when we have so many births that we've seen both 15 boys and 15 girls, then this approximation should be fine for most purposes. And from the normal distribution we know that if we take our mean value plus minus 1.96 times the standard deviation, then we have 95% of the probability mass. So if we go back and look, we have, if we go out to 1.96, so that would be here, and 1.96 here, so 1.96 standard deviations to each side, then the area below the curve in this area will have a total area of 95%, so 0.95. To use this this fact, then what we're really interested is in the pi. So this interval is some unknown interval. We don't know what pi is. We don't really know what sigma is either, but we'll get back to that. So we cannot really use this interval for anything. But if we kind of turn things around and say, okay, let's use our data to make a random interval, where we say we take the pi hat and then we look at minus 1.96 times this sigma divided by square root n, and so plus minus that, then we get a new interval here, which with 95% probability will contain the value of pi. So pi is a fixed value, and we make a random interval based on our sample, and this random interval contains pi with a 95% probability. And now there's only left that we don't really know what sigma is, but we have a formula for the standard deviation in the population that tells us that that's just the square root of pi times 1 minus pi. So pi is the probability of observing a girl, and 1 minus pi is the probability of observing a boy, the proportion of girls, proportion of boys. Of course, we don't know what this is, but we can plug in the estimate that we have from our data, the pi hat that we observe from our data, and say that's probably a good approximation of the true value of pi. And then we call this the observed standard error, SE, so SE for standard error. And then we have this formula for it, which is now everything is something we can calculate from our data sample. And then we have our 95% confidence interval is given by the formula in the bottom here. So this final part is a formula with ready to plug in numbers from a given data set. Now we call this a 95% confidence interval, and obviously we call it 95% confidence interval because we constructed it in such a way that we are 95% confident that the true population parameter is contained in this random interval. But why use 95%? We could use something else. The 95% is called the confidence level, and the other values can be used, like 99% or 90%. If we look at the reverse probability of 1 minus the confidence level, so that would in this case be 5%. That's called the error probability or the significance level, alpha. And if we want to construct a confidence interval with some other confidence level, 1 minus alpha. So let's say we want an error probability of 1%, so that corresponds to a confidence level of 99%. Well, then we just need to take the 1% error probability and divide it into 2, because there's an error both to the left and the right. And then we get a value from the normal distribution, so we have to look that up either in software or in a book, a table, and then we could find the value 2.98 if you look up this tail probability in the normal distribution. And then we can calculate the standard error, that's just with the formula before, and we just take pi hat plus minus this critical set value that we looked up in a computer or in a table, type the standard error, and we have a confidence interval. And finally, with all these precise decimal points, etc., in statistics, a lot of time we just are a little bit loose and just say, well, an approximate 95% confidence interval is just given by the estimate plus minus 2 times the standard error. And this is a very general rule of thumb that we use often. And finally, let's have a look at a real data set where from a dataset from Germany all the way back from 1922, so it's almost 100 years old by now. There was a total of 437 female births out of the 980 placenta previa births, and so the sample proportion is given by this percentage, so it's or this proportion, so it corresponds to 44.6%. And the standard error is just plugging in the numbers in the formula for the standard error and getting a standard error of 0.016, so 1.6 percentage points. And so the 95% confidence interval is, again, take the standard error here and multiply by 1.96, so that gives you kind of a margin of error, and you add and subtract that to your point estimate, and that gives us finally a confidence interval of 0.415 to 0.477. And one thing we notice is that the population value of 48.5% for normal birds, for non-placenta previa birds, is not contained in this interval. So we're saying that we're 95% certain. With 95% certainty, the true population value for placenta previa birds is somewhere in this interval, and it's not containing the normal value that we might expect if it was unrelated to placenta previa, was unrelated to the gender of the child. So in a later stage, we will say that such a result is significant, that we have a significantly different sample proportion than this predetermined value that we were kind of maybe expecting if there was no relation between the condition and the gender of the child. And we say that it's significant at the 5% level because we've made a 95% confidence interval. Notice that here at the very end that if we'd made a 99% confidence interval, well then this interval actually contains the population proportion 0.485 is just inside this interval, and so this result is not significant at the 1% level. And that's all for this time. Thank you for listening.